Hello and welcome to the Introduction to Chemical Equilibrium module. This is part of the Chemical Equilibrium series. In this module, we're going to cover chemical systems, talk about physical change versus chemical change. Then we're going to discuss reversible reactions using some of our knowledge from before, and then incorporate this all into understanding equilibrium equations. So first off, I want to start by discussing a system versus surrounding. So this will be very familiar to work that you've already done in chemistry. So a chemical system is the chemicals involved in the actual reaction. So I'm going to use some arbitrary chemicals here, such as A plus B, our reactants, forming our products C plus D. So before we move forward, I want to make sure we have some key terms down: reactants and products. So keep this terminology in the back of your mind as we move forward through this module. So our reactants and products here, or the chemicals A, B, C, and D, are part of the actual reaction. So they form our chemical system. Now, on the contrary, we have a chemical surrounding. So these can be anything around the reaction that aren't participating. So they're not participating in our reaction. So again, I'm going to use some arbitrary chemicals. Take, for example, E, F, and they're just floating around. So these can be pretty much any other chemical in infinity that are surrounding the reaction, but they're not partaking in the reaction themselves. So we have a chemical system, A plus B to C plus D. Now, instances where we might see this are reactions in the atmosphere. Take, for example, ozone reactions. Now, we have a lot of nitrogen gas within the atmosphere, and they may not partake in a lot of ozone reactions. So our ozone reactions and the chemicals involved in that would be our chemical system, whereas nitrogen, for example, may be part of the chemical surrounding. Now let's have a look at chemical systems in a little bit more detail. So a quick review: our chemical system are the chemicals involved in the chemical reaction. So let's have a look at A plus B, our reactants going to our products again, there's that term, to C plus D. So chemical systems can be divided into either being closed or open. Now, a closed chemical system is something that's contained within a certain space. So what I like to think of is just putting in our reaction inside a box. So it may be happening in a closed container, a closed jar, closed test tube. So within this circumstance, nothing can enter, nor can anything leave. So nothing will enter, nothing can leave. So we have no chemicals added to our reaction, nor do we lose any chemicals. So we can't add any A or B, or add any C plus D, nor are we losing any of our chemicals to the environment. And that's where an open chemical system comes into place. So we have an open environment. So I'm going to take away this box, and what we can see now is that chemicals can be added or they can be lost. So we can lose C and D to the environment, so it can just go off, or we can add A and B. But also, to the contrary, we can also have an increase in C and D if it's already in the environment we're doing the reaction, or we can have a decrease in A and B as it dissipates into the environment. So again, I'm going to use an example, say a reaction taking place within the atmosphere. We can increase A and B, or we can decrease it because it can be lost to the environment, or we can also add C and D, our products, or we can lose it. But the key thing I really want everyone to make apparent is closed reactions, something happening within a box. where nothing can enter, nor can it leave. So we're going to have no loss in chemicals, nor no addition of any chemicals. So I want to keep this in the back of your mind when we start talking about reversible reactions and reactions that go to completion and ones that don't. Now, I want to do a review of your previous units. Very quickly, we're going to talk about physical change. So physical change is when our products do not change. So we're getting no new substance. This is very important. So take, for example, our water reaction down the bottom here. What we have is H2O in a liquid going to a gaseous state. So we have no new substance formed. We still have H2O, water, but we have a change in state. And this change in state can go from solid, liquid to gas, and this is dependent on energy within a system. And within the example below, we've gone from a liquid to a gas. Now, an important thing to note with physical change is all physical changes are reversible. So for this instance, we could go back from a gas to a liquid. Now a review on chemical change. Chemical change, on the other hand, can be both a physical property change, so liquid, gas, water, think about that, plus a chemical property change. So what I mean by chemical property change is that a new substance is formed. Think of the example below. I've used some arbitrary chemicals here, or some arbitrary values. We've gone from A, which is split into B plus C. We still have the same chemicals, as you've learnt before, balancing a chemical reaction, but we've created new substances. So take, for example, a water reaction where we're splitting water, and we're getting 2H2 plus O2. So we still have the same chemicals because it's balanced, but we've created two new substances. We've created hydrogen gas plus oxygen gas. Now, as I said before, we have a physical property change. It doesn't have to happen, but it can. But a chemical change has to happen for it to be notated as a chemical change. Now, comparison to our physical change, only some of our chemical changes are reversible. So what I mean by reversible is, as we said before, it can go back to the beginning. And this is what we're going to discuss now. Reversible reactions. Now, previously, you guys would have explored just a forward reaction. So again, I'm going to use some arbitrary values. A forward reaction of A plus B going to C plus D. So we have reactants going to products. That is our forward reaction. This is something you guys would have typically seen and been typically working with. Now we're going to explore a reverse reaction. So a reverse reaction is nearly identical to our previous reaction. We still have our same reactants and products as before, but instead of our reactants going to our products, like our forward reaction, we now have our products going to our reactants. So what I'm going to do is reverse the arrow here. Now you can get questions where it might be breaking down or showing the reverse reaction. Another way to write that would be C plus D going to A plus B, and that is identical to that one there. But for this example, what I want to show is just the arrow being reversed. So we have our reverse reaction. So what do we know about these reactions? Well, they do not go to completion. And what do I mean by that? Typically, you guys would have been working with the forward reaction. And with that, what we mean is all our reactants, so A plus B, would be used up to form C plus D. And that would be the end of our reaction, and that's complete. But because we have a reversible reaction, C plus D can now go back and form A plus B. So the reaction is continuing, and this cycle can continue. A plus B can go back to C plus D. Now, one way we like to denote these reversible reactions is using this arrow here. So what we know, A plus B, our reactants, will go to our products as the forward. We also know our products can go back to our reactants. And the important thing is these reactions do not go to completion. Right, now that we have a basic understanding of reversible reactions, I want to talk about equilibrium. And whenever we talk about equilibrium, I want everyone to think about something being balanced. So equilibrium, by its definition, is a state of balance between opposing forces and actions. And now, what are our opposing forces that we need to balance? In regards to chemistry, we have our forward reaction, as well as our reverse reaction, which we're balancing. But what are we really balancing in regards to these reactions? We're balancing the reaction rate. So the reaction rate is how fast products are produced in our forward reaction, and in our reverse reaction, it is the opposite because it's going backwards, is how fast our reactants are produced. So again, I'm just going to write out what our forward reaction is. A plus B, again, just arbitrary chemicals, going to C plus D. So the rate of reaction here, and our reverse reaction, we have our reactants and products, but instead it's going from products back to reactants. So we're balancing that reaction rate. So I'd like to draw a little bit of a scale so we can think about what's happening here. And we're going to discuss this a little bit further in detail in another module, but start thinking about balancing our reaction rate. So we're just balancing our forward reaction and our reverse reaction. We're balancing the reaction rate. So we're trying to get to a point where our reactants and our products are made at the same rate. But what is some of the requirements we need for equilibrium to happen? We've discussed before about an open and a closed chemical system. And this is where our closed chemical system comes into place. So we need to make sure we don't lose, so no loss of reactants and products. So let's draw our A plus B. It's a reversible reaction going to C plus D, and it's within a box. So we're not losing any of our reactants, nor are we losing any of our products. So what that means is our products, these ones, can go back and react to make reactants. And so the second requirement is we have constant simultaneous forward and reverse reactions. And what I mean by constant simultaneous is we may be having forward reactions taking place, so that A plus B to C plus D, we have forward reactions taking place, but at the same time we have the reverse happening. So we have C plus D going to form our reactants. And this is what we call, or start to think about, when we think of a state of dynamic equilibrium, is what our reaction will reach. So dynamic equilibrium is when our forward rate equals our reverse rate. And think back to what I was saying about equilibrium, wanting to balance on our scales. Dynamic equilibrium is when that forward rate balances with the reverse rate. So a way to think of that is at the same time products are being made, they are being used, and the vice versa. At the same time reactants are being made, they're also being used. And this is called a steady state. So a steady state of chemicals being produced, and those same chemicals that are being produced, our products, are also being used up to create our reactants. So I'm going to try and draw it out. So we have A plus B going to C plus D. So at the same time our products are being made, so our reverse reaction, so C and D will form our products, they're also being used up. And as a result, at the same time reactants are being made, our forward reaction, our reactants are also being used up to form the reverse. So again, this is our steady state. Steady state is where our forward rate equals our reverse rate. So one way to think of it is our concentration of our reactants isn't changing, nor is the concentration of our products are changing, but they're reacting at the same rate. So as something's being destroyed, something's being formed, or as something's being formed, it's also being destroyed. So another way to look at this is through the principle of microscopic reversibility. So this principle talks about continuous activity on an atomic or molecular level, where we have no net change in the concentrations, so again, going back to no net change in reactants and our products, but our reaction is taking place. So whatever is being done is also being undone at the same rate. Now, I've talked about steady states. What I need to emphasize is that reversible reactions have steady states because they are continuous. But irreversible reactions don't always have a steady state. So steady state is the requirement that the reaction rate stays the same. So again, we'll use the example, A plus B going to C plus D. Because this reaction, let's say, is reversible, so I'll denote that as reversible, C plus D, once it's formed, can go back and form A plus B. So we have a forward rate of reaction taking place, as well as a reverse. So as some's being created, some's also being destroyed to form the reactants again. So we have a steady state, an endless cycle. Whereas irreversible reactions, so I'm just going to use E to F for this example, don't always have a steady state, because once you use up E, there's no more reaction taking place. You've formed all the F. So there is no steady state achieved. But if you kept on adding E, so you kept on just adding more and more E to the reaction, that it kept on taking place and kept on continuing, you'd have a steady state. So think of reactions in the atmosphere, or think of a reaction where you might be in the lab and you're continuously adding more and more reactants, so you continuously get products. The moment you stop adding reactants and your reactants get all used up because it's irreversible, they're not being formed again, you've gone to completion and there is no reaction taking place. So you have no reaction rate and it's not at a steady state. So keep this in the back of your mind moving forward. And in our next module, we're going to start discussing equilibrium reactions in a lot more detail. So Thank you for watching.